UCSF, came to UCLA as a resident, the chief resident in psychiatry and then cardiology, and has been practicing cardiologist at UCLA for a while now. More recently, she's become interested in the leader in the field of sort of comparative medicine, or researches of comparative medicine. She's the author of a book called Ubiquity, which is a great reading. She's helped us put together our evolutionary medicine program and is teaching sort of a clinical course in evolutionary medicine now to EEB students and students from all over campus. And today is going to talk about translational evolutionary medicine. Thanks, Barbara.
Great. Thanks. Thank you. Thanks, Dan. And I'm really so excited to be here. I mean, people say that and they don't mean it, but I really, really mean it, because this summer, sometime, I think around July or early August, I got a letter that it was official, and that I was a member of this department. And it actually fulfills a secret lifelong dream of mine to be an evolutionary biologist. And so I consider myself unbelievably fortunate, actually pinching myself, living the dream. So really, really happy to count myself among you. So in thinking about what I might talk about, there are a number of directions that I could go. I think some people here have heard the sort of the basic talk that I've given about how a clinical cardiologist ended up talking about animals and evolution. And I think I'm going to cover that. I am going to cover that. But I thought I would start out by a much broader question, which goes to whether or not evolutionary medicine is in fact translational. So to answer that question, we have to first answer two questions. First, what is translational medicine? And by what is translational medicine, I mean, what the hell is translational medicine? Because that term is used constantly, broadly, and promiscuously. And then what is evolutionary medicine, which I think is a really fair question, because this is an emerging field, and it's important that we work on developing definitions for this emerging field. So one kind of classic definition for translational research involves the effective translation of the new knowledge, mechanisms and techniques generated by advances in basic science research into new approaches for prevention, diagnosis, and treatment of disease. So this is kind of the super classic translational idea, from the bench to the bedside, sort of harnessing the power of discovery at a very reductionistic level, and conceiving of experiments which are constantly informed by the application to a human life, to a patient life. So that's a super classical definition. This is an old kind of schemata regarding bench to bedside, but it is this classic translational medicine is centered on this collaborative, synergistic scientific efforts. And these words, I'm going to show you sort of the definition of translational medicine that comes from the national academies and from the Institute of Medicine and the NIH. And you see these words, collaborative, interdisciplinary, synergistic, over and over again. But essentially, the idea is to catalyze what's happening. Can you see, is that? No, I don't think that laser pointer is working. Anyway, to catalyze what's happening over there, thank you, with basic research at the bench, and using this translational approach, accelerate all the way to a treatment. Now, I have to say that one of the aspects of collaboration that seems to be very important and informs a lot of the literature is collaboration with industry. And there is this kind of inherent commercialization, the potential for commercialization that you'll see is the language about translational medicine is infused with. But you basically can't do anything now unless it's translational. The NIH has identified translational research as its priority. There are at least now more than this, 64 clinical translational science award-funded academic centers with well over now $500 million, which is earmarked exclusively for translational research. The European Commission has comparable budgets. There are now multiple peer-reviewed journals which are dedicated exclusively to the translational approach, whatever that is, and it is now become a requisite buzzword for pretty much anything. It's interesting in just reviewing definitions for this lecture how the two words that come up are application, So taking whatever the discoveries are and bringing them to the clinical patient, and commercialization. Again, harnessing this knowledge from basic sciences to produce new drugs, devices, and treatment options. Drugs, and this is language from the NIH, so drugs and devices is very high up there. Emphasizing the interface between basic science and clinical medicine. And ultimately, the endpoint is the production of a promising new treatment that can be implemented and commercialized, and that is actually explicit. And part of that simply has to do with where the money's going to come from. It is very expensive to develop new therapies. It takes almost $1 billion and over a decade to a decade and a half typically to develop one new drug that is marketable. Yes, the drug companies cry that R&D is so expensive and hence the markup, but in fact it is a very, very lengthy and expensive process to develop a new drug. The traditional kind of pre-translational concept involves first understanding the basic pathobiology, identifying potential targeted agents, going through preclinical toxicology, classic phase 1, phase 2, phase 3, and then ending up ideally with something that's marketable, and that's the goal. The accelerated translational approach works in this kind of reverse, thinking about this clinical goal and working backwards. And again, this is the idealized concept that the process is not simple, it's not linear, it's iterative, it's driven by this goal. There's reverse engineering, and again, words like collaborative. There's more to come like that. And just for your interest, several years ago, the Bayh-Dole Act actually accelerated things significantly by allowing universities to patent research discoveries and its potential for wealth creation for faculty members. And as a result of that, I'm sure many of you are aware of, that has actually helped a lot of the development, particularly of devices in my field, by academics. Words like collaboration among pharma, academic, government, sharing, complementary, integrated, collaboration again. And this from the NIH, just like a sampling of other descriptors for translational medicine: shared, cross-institution, shared continuous improvement, broad, transparency, anyway, and balanced. So this is, there are, however, other fields that are using this term translational. One of the main applications of the translational approach right now is in health sciences and health services research. And so translational has come to also mean taking what has been discovered through clinical trials and making sure that target populations are gaining access to the benefits, so it's an implementation issue, making sure that there are cultural boundaries that are recognized, and that there is interdisciplinary and interprofessional dissemination of the information. So that's an alternate definition of translation. But the definition that I think is more relevant to evolutionary medicine is, and more enticing, is this idea that we can think of evolutionary medicine as a basic science, and that the insights that we gain through this approach, which we are going to collaboratively develop as the field emerges, can then be applied and targeted to deal with specific clinical problems. Two sample definitions of evolutionary medicine, and I went through Nessie and Stearns and Gluckman and all the kind of the people who've written big books about evolutionary medicine. Evolutionary medicine is an approach to contemporary clinical dilemmas which applies evolutionary principles to help further an understanding of a given disorder and to accelerate the development of effective therapies. And I'm going to give you some examples of how I think this might work. It is also the application of evolutionary principles to yield new therapeutic approaches for cancer, infectious disease, autoimmune disorders, heart failure, metabolic disturbance, psychiatric syndromes, and many, many others. Already, evolutionary medicine, or people who are using this approach and calling themselves evolutionary medical practitioners, have applied this approach to disorders including congestive heart failure, which I'm going to focus on later in the talk, metabolic syndrome. Everybody is familiar with metabolic syndrome. So this is a disorder that typically it's increasing significantly in our country due to obesity and diet. And metabolic syndrome is, we see patients who tend to have truncal obesity, that is they're gaining that tire around their tummies. They have an elevated triglyceride. They may have glucose intolerance, so it's like a pre-diabetic state. Their cholesterols are abnormal. It's a metabolic condition that is highly associated with accelerated atherosclerosis, so we're talking about heart attack risk, stroke risks. It's a very big issue. And yesterday I was listening to Steve Stearns, who is teaching an evolutionary medicine course at Yale right now, has just put on the web these about 14-minute lectures on topics in evolutionary medicine, and one of them is on metabolic syndrome. And he describes the epigenetics of metabolic syndrome, and he basically uses the concept that a fetus who is gestating under conditions of calorie deprivation will have that the epigenetics associated with calorie deprivation seem to be associated with the activation of genes later in life, which are associated with the tendency to towards obesity and metabolic syndrome. So that's a well kind of laid out, he's very elegant in the way he talks about that, way of using fundamental evolutionary principles to understand a very important clinical condition that has huge adverse effect on massive numbers of people. I'm going to talk to you later about sudden death syndromes and how we can think about this problem from an evolutionary context. Probably many of you, when Athena Actipis came, Athena is an evolutionary biologist, and she and her husband Carlo Mali were up at UCSF until last year, and they had a program looking at the application of evolutionary principles to cancer. And she has some really interesting ways of thinking about metastasis and using ecological models of dispersal and trying to ask questions like, if a tumor is in fact not a group of cloned cells, which of course it's not, it's a heterogeneous clump of individual cells, each with their own genetics and individual needs, how would abundance of resources versus scarcity of resources for that population affect the tendency to disperse / metastasize? Again, a very, I think, creative and novel kind of hypothesis. Whether it's accurate or not, I don't know, it needs to be tested, but this idea that one would think like an ecologist about a problem which is very relevant to human medicine, I think is to be applauded and is a very interesting, a good example of this kind of approach. And I think probably everybody here is, at this point, familiar with the fascinating and emerging connection between cleanliness and the issue of autoimmune disorders, the hygiene hypothesis. And of course, this is again an emerging area where we don't know how ultimately true it will be for all of these disorders, but there seems to be a connection between, let's say, underexposure to pathogens that our immune system, the mammalian immune system, evolved to encounter, and the emergence later in life of Crohn's disease, severe allergies, ulcerative colitis, et cetera, all these autoimmune disorders. And by the way, this kind of a theory, the hygiene hypothesis, immediately, I think, becomes translational because you can go from theory to developing a plausible intervention, and that would be where sort of the traction is. Precocious puberty is another one. I'm sure everyone, I hope everyone is familiar with this issue that our girls in this country are reaching puberty, and our boys actually are reaching puberty earlier and earlier, and there's a significant question about why that might be happening. There are some contemporary issues that might be influencing that. The rise in obesity in both boys and girls could be part of it. Others have speculated that endocrine disrupting chemicals in the environment. But there's another way of thinking about this, that apparently in dangerous environments, in certain animal models in dangerous environments, there is a tendency for reproductive viability to happen earlier, and that seems to make sense in a certain perspective. And there have been, some interesting theories, not, I don't think proven, but theories looking at dangerous human environments, and do we see more precocious puberty in those environments, and what does dangerous mean, and all of those kinds of very difficult questions, but a wonderful target, I think, for this evolutionary approach. Obsessive compulsive disorder, actually, and other psychiatric syndromes, these are, I think, wonderful targets for thinking from an evolutionary perspective for a couple of reasons. First, because up until very recently, there was very little attention paid to animal mentation. And we can thank Descartes for that maybe, but even more recently, and there are people in the audience who are so much more expert on the history of this particular science than I, but it was remarkable to me in researching the book to learn that up until the early 80s, 1980s, many textbooks of veterinary surgery did not endorse the existence of somatic, of physical pain in animals, such that there were very elaborate instructions about restraint in advance of doing, a torsion repair or, a laminectomy or whatever, but nothing about analgesia or anesthesia. So that is that's 30 years ago, right? So that's very, very recent. So if 30, 35 years ago, conventional mainstream veterinary medicine wasn't acknowledging physical pain, you can imagine the barriers to accepting the potential of psychopathology. So you need, yes, there's physical pain, you need, yes, there's some form of sentience or whatever you want to call it, and then you have to get to psychopathology. Well, we now know, and I certainly have been spending a lot of time in the veterinary space, that psychopathology is very common in animals. It is well known in dogs and companion animals, dogs and cats, to have all kinds of compulsive disorders. There are actually, there's a syndrome which is seen in Doberman. It's called a flank sucking disorder or blanket sucking disorder. And this is a compulsive disorder. Nick Dodman, who's a DVM PhD at Tufts, actually identified canine chromosome number 7, which connects to the cadherin molecule, which is seen in affected Doberman and is absent in the non-affected Doberman. So there are horses that engage in very compulsive stereotypic behaviors. Certain species of bears, for example, in captive environments are polar bears, or the classic ones are notorious for pacing. It's almost a cliche, the pacing polar bear. I'm told by zoo veterinarians that most polar bears in captivity in North American zoos are on fluoxetine or another SSRI. Fluoxetine is Prozac. And there are many interesting parallels. I'm not going to get too tangential, but one I just think fascinating comment that was said to me by a zoo vet is that if you watch individual polar bears pace, they have specific numbers. They count their number of steps that they have. So one polar bear paces 13. And anyway, I just think that these kinds of connections between human and animal compulsion is fascinating and becomes an interesting target to think about, and especially juicy and enticing, because until very recently, the concept of compulsion, self-injury, an eating problem, etc., in non-human animals was just not on anybody's radar. Okay, and we can talk more about that maybe or maybe not later. And actually, that ties into hoarding as well. As we've got so many animal experts here, it is no secret to you that many species of animals hoard. There are granaries and all kinds of stockpiles of food that animals indulge in, and this kind of problem, which on the human side is actually a DSM-5, problem, has roots, I suspect, hypothesis, in animal hoarding behaviors. And what a wonderful target for looking at mechanism for trigger and asking, are there conserved mechanisms that can help us understand this psychiatric problem? Fainting is one that since I'm a cardiologist, I was one of the first clinical syndromes that I looked at to ask, can we enlighten the conversation about fainting by thinking comparatively? And when you think comparatively, you're thinking evolutionarily. So fainting, how many people here have ever fainted? Okay, if you're not shy, and if your faint involved fear, pain, seeing blood, anything like that, and you want to share, can you just in one sentence share what happened? Nobody? Okay, then I'll share mine. I fainted twice. The first time I was a third-year medical student. I was on my OBGYN rotation, and I had been up a couple of nights. I was sick. I was dehydrated, and I think, helped with 2 or 3 vaginal births, and this was going to be the first C-section, and I'm short, so I stepped up on the little stool, and I was standing there, and my resident told me to retract as they were retracting to expose the gravid uterus, and I did what I was told, and there I was, standing there, and she took her scalpel, and she cut into the uterus, and there was this, I just didn't expect it, this huge kind of gush of this hot fluid that just poured over the back of my hands and my forearms. And it was, even now, I'm getting a little bit vagal thinking about it, and it was so shocking to me that I fainted. And I had a true, what we call a vasovagal syncope. Syncope is the medical word for fainting. So what we see in some people, some are more, juveniles are more predisposed than older folks. There's probably a tendency for some individuals to be more vagal, that is more parasympathetic than sympathetic. But in response to fear, danger, threat, while fight, flight, that is sympathetic autonomic activation is the rule, there are certain situations where human beings will, instead of having a fight, flight, will actually have the opposite arm. There's withdrawal of sympathetic input. We have vagal dominance, parasympathetic dominance, and that leads to bradycardia, which is a slowed heart rate. And that is the physiology of fainting in response to hearing bad news. Getting left at the altar, losing your life savings with the roll of a dice, that kind of emotional fainting. Okay, so the question is why? That seems like a really bad kind of arc to have in your autonomic repertoire. But it turns out that there are many species, particularly juveniles, who can use fainting type behaviors, a bradycardia, which slows an animal just as it slows a human who faints, and that slowed heart rate can be a form of kind of crypsis and can allow, for example, an aquatic animal to stop moving and creating either vibration or the electrical impulses that some underwater predators use to track prey. So one hypothesis, and of course we need to continually identify these as hypotheses, would be that that arc is life-saving under certain conditions, that the potential for a highly threatening situation to, if fight-flight is not a good option, to have this super slowed down, bradycardic, parasympathetic response, that might be very life-saving. And the hypothesis is that we have, that is conserved across at least mammals. There are many juvenile mammals who do have this heart slowing in response to threat. There was a study that was done of some fawn, I forget, it was like red-tailed, white-tailed deer, some kind of deer species, and they put telemetry on the fawn, and then the scientists played recordings of wolf howls. And when the wolves howled, there was this very reproducible, profound bradycardic response that is very significant heart slowing on the part of the deer. There was actually a natural experiment that happened back during the first Persian Gulf War. There was, you'll remember Scud missiles. Iraq was sending Scud missiles into suburban Tel Aviv and actually the outskirts. And there was one of these evenings. Oh, and when the Scuds would fire, they had sirens. There were sirens that would blare, and all the television stations would suddenly start blaring the sirens, and the radio station. And there were several women, a bunch of women were, but in one hospital, several women were in labor at that time, and they were wearing the fetal monitor. And all of a sudden, there was a Scud alert, and the sirens blared, and the nurses who were watching the fetal telemetry noticed there was this sudden and persistent bradycardia on the part of the babies. So that's kind of a natural experiment of either the maternal catecholamine activation triggering this gestational effect, or maybe the infant, the soon-to-be infants actually hearing it. So that's a human corollary. STDs are another really kind of, I think, juicy target. It should not come as a surprise. I'm not sure what the drum roll was, but the juicy, yeah, okay. Oh, okay, Dr. Fessler. But actually, when you think about it, animals, of course, wild animals have STDs. They, not all species are promiscuous and have multiple sexual partners. I'm sure people here could probably identify those that are monogamous, but I would say that it's probably more the rule that animals will have multiple sexual partners. As per my last Google search for condom use in animals, they do not practice safe sex. And so, moist mucous membranes, multiple sexual partners. Of course, there's constant passage of pathogens. Why wouldn't there be? Viruses, bacteria, et cetera, et cetera. And so it should not be a surprise at all that STDs happen, and they happen commonly in animals. And the passage of pathogens can be, you can have colonization without infection like anything else, but in certain conditions they can become pathological. In the book I write, one chapter is entitled The Koala and the Clap. And it is actually koala and chlamydial infection, not gonorrhea. The clap is a historical term for gonorrhea, but I could not resist the alliteration of koala and the clap. But the point is that animals do get STDs. And looking at why certain populations are less susceptible why, or more susceptible, I think offers this actually very sort of hiding in plain sight model for studying human populations who have multiple sexual partners, aren't practicing safe sex. And there are many, many, I think, great questions that can emerge by looking at, from an evolutionary perspective, at STDs. And of course, I think the antibiotic resistance story is well known to everybody. Well, what are the evolutionary principles that we can apply to clinical scenarios? And I guess what this slide is moving toward is evolutionary medicine evolutionary biology? And I will ask that question, and I'll step out and I'll say, I think it is. You know, I'm in kindergarten, let's say, as an evolutionary biologist among you folks here. But I would say that we could look at all of these principles, and by looking at common, important human medical problems, congestive heart failure, pneumonia, HIV, etc., enhance, amplify, expand the discussion about the disease, the human disease, by bringing these terms into the discussion. Now, I will tell you that with the exception of the term adaptation and maladaptation and defense mechanisms, and, sorry, this one, tolerance versus resistance, medicine doesn't use these other terms. And I can say that with confidence because I've spent almost 20 here at actually 25 years here at UCLA on rounds as an intern, a resident, cardiology fellow. I've gone rounds at the VA and the General Hospital and tertiary. And I've talked about many, 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 many human diseases. And now when I am thinking about them from an evolutionary perspective, these kinds of questions enter into my mind during the discussions. But in all of my time on rounds, with the exception of the use of the term adaptation and maladaptation, tolerance versus resistance, and defense mechanisms, people don't use these terms, and virulence. Okay, so something as powerful as thinking about mismatch as a part of the explanatory system it's amazing that that's not done. So I think this is a real opportunity for all of us to become teachers of physicians and medical students about this approach. Well, how are we going to make this happen? How are we going to make physicians a little bit more like evolutionary biologists and get evolutionary biologists to begin thinking in this translational way? That is, to begin thinking a lot about how what they're doing applies to the human condition and human health and disease. Frankly, I think you guys are doing that already. You're human beings, and we all have health issues, and we're all aware, I think, about medical problems. And my guess is almost everyone who is working in your field thinks about the connections back to the human case. But it's not true in reverse. So what our challenges are to, number one, expose the medical community to evolutionary biologists and to evolutionary principles. And number two, and this is probably the most important, to demonstrate, we have to prove, we have to show that the application of these principles will lead to novel hypotheses, and then we've got to show them where the money is. We have to go from hypothesis to something, to a treatment, to an intervention, to something that works. I have to say that I started, when I was writing the book, well, let me take a step back and say that I always liked evolutionary biology as an undergraduate. I, took it and I was fascinated, like a lot of physicians are. But, once you get started working as a doctor and you're busy, you're just busy. And it's not that you don't want to do stuff. Occasionally I'd hear about stuff up here at UCLA, but I would never have taken the time to do it. And it wasn't until I was writing the book with my co-author, Catherine Bowers, and she started telling me about these Beck lectures. Oh my God, I went to this Beck lecture. She discovered it. I'm not sure how she discovered it. And so I started sometimes leaving UCLA and trekking up to Beck. That I actually met Dan. I think you were sitting a couple of chairs behind me. And and it was completely fascinating, and those lectures are. And I think most of my colleagues would find it thrilling to sit through many of those lectures. The problem is coming up to North Campus is hard. And by the way, at the medical center, we consider anything north of Charles Young North Campus. Apparently there's some internal differentiation that's different than that. But I think the real barrier, frankly, is time and a compelling reason to be there. I had a compelling reason because I was writing a book. My colleagues need a compelling reason to meet you guys, and once they do, I think they would find it very thrilling. I now am involved with a number of activities. I ended up attending this evolutionary medicine week in Maine that was put on by Nessent. Randy Nesse and Steve Stearns and Peter Gluckman and Andrew Reed, a lot of people were faculty there. And they spent a lot of time, I love them, they have been my teachers, but they spent a lot of time talking about creationists and the barrier and how physicians don't understand evolutionary biology and are against it. And I would beg to differ. I think that, and I count myself in the age category of them, that is the north of 50 group, but I don't really think there's a big problem with physician creationists. I'm sure there are some, but I don't think that's the barrier. And I don't think that there is that kind of ignorance that there used to be. I mean, look at the undergraduates that you teach, right? Probably half of them are pre-med, maybe more. So they're coming through this evolutionary biology background. That's not the barrier. The barrier is time. The barrier is a proof of concept project, let's say. We need a reason for them to be there. The other side of this is we need to expose evolutionary biologists to the medical community and to medical scientific issues so that if you're working on something and you may not even know what the human medical application is, there are so many applications in psychiatry, in cardiology. It's not all antibiotic resistance and zoonotic infections. And to encourage this translational way of thinking, and then to partner with research collaborators in medicine. And I think that's why you guys are all here today. Here at UCLA, some of the faculty here, including Dr. Glemstein, Dr. Fessler, Dr. Nonax, where I just saw Jamie. Oh, hello, Dr. Smith. Pamela. A number of faculty are involved in this effort to bring our schools together, the Department of Medicine, the School of Medicine, and Life Sciences. We have started Evolutionary Medicine Month. That started a couple of years ago, where we take February and we've co-opted several of the internal medicine grand rounds. And we've invited evolutionary biologists from actually around the country and now around the world to give grand rounds to our medical students and our interns and our residents and our internal medicine faculty. After they give their grand rounds, and grand rounds, by the way, is when everybody sits in an auditorium. Work rounds is when you're walking around the hospital, but grand rounds is like this, but big. After that, we have our evolutionary biologist, we embed him or her into rounds with the team. And the evolutionary biologist walks from case to case, room to room, hears the cases presented, and offers an evolutionary perspective. This is modeled on what we do when a guest professor comes from another institution. We let them be the guest attending, but we're just saying they don't have to be an MD to have information and insights that are relevant to the cases. And that's been part of our project. We've been conducting special events. We showed Contagion a couple of years ago, and we had a panel of evolutionary biologists and anthropologists talk about it. We showed World War Z a few weeks ago. And of course, I'm sure you're all aware, we've started this evolutionary medicine minor. Nationally, there are several evolutionary medicine programs around the country. Duke has one, Arizona State has one. I'm sure there are several others. There are a few people, I would say a dozen or so, giving evolutionary medicine courses that are part of a little consortium that I know through Nessent. And Nessent has a working group dedicated exclusively to infusing evolutionary content into medical education, and I'm part of that working group. So, all right, but is this translational? Is looking across species, is looking at ecosystems instead of individual patients, is looking at the ancient past. Does that give us insights that can generate novel hypotheses that are testable, that can lead to new treatments and cures, let's say? And that's the question, and that is actually the challenge of this entire enterprise. If it's going to work, it has to work. So, how did I end up getting here? I'm going to give you a very brief version of how it is that I'm standing here today, and use that to sort of segue into what I think is an excellent proof of concept project for evolutionary medicine. So 10 years ago, I was happily practicing cardiology. It was the old building, taking care of heart attacks and atrial fibrillation and high cholesterol, et cetera. And then I had this cool opportunity to go to the local zoo and help do some cardiac imaging on some of their great apes and then their big cats and a bunch of their animals. By the way, just zoos and aquariums across the country are staffed by board-certified veterinarians who take superb care of their patients. But from time to time, they do reach into the human medical community for for assistance and collaboration, and I was one of the lucky MDs. So I had a chance to rule out an aortic dissection, which is a torn aorta. That's the disease that killed John Ritter recently, 10 years ago. Lucille Ball died of aortic dissection, Albert Einstein. It's an important human medical problem. It's a leading killer of Western lowland gorillas in captivity. I listened to assessed a heart murmur in a macaw, ruled out constrictive pericarditis, which is in a sea lion, and I'm listening to, yeah, this is a great picture, but I'm listening to a heart of a lion after a procedure, a collaborative procedure, where we removed about 700 cc's of serosanguinous fluid from her pericardial sac. It was this really cool collaboration. This was like, veterinarians, physicians, veterinary cardiologists, human cardiologists, anesthesiologists, and it was successful. I always like this one because you have to spot the tail and you have to spot the paw. Otherwise, the procedure was, of course, the same. Very conserved pathophysiology. But one of the first cases I did was a chimp who had a facial droop. She woke up with a facial droop, and the veterinarians asked if I'd do my procedure. When a human being wakes up with asymmetrical face, we think about a stroke. And you look, one of the first things we do is look in the heart to see if there's a blood clot or a tumor or atherosclerosis that embolize that causes stroke. So I went in there, I put the probe in, and I saw this. A 4-chambered beating heart, left ventricle, left atrium, right atrium. But immediately I noticed the pathology. There was thickening, infiltration of the free wall, the LV and the RV. The septum was thickened, the atria were large, and in here, in the right atrium, were these balls. Do you see these bouncing balls? These are blood clots. These are thrombus. And I immediately recognized this pattern, biatrial enlargement, as an infiltrative cardiomyopathy that I'd taken care of in many human patients. I'd seen a case almost identical to this several weeks before. And I had this aha moment, which was kind of a surprise, something that I've been taking care of in human beings in a very high-tech environment, referring patients like this for heart transplantation and for biventricular pacemaker, et cetera, that this happened in a chimp. Immediately I was surprised in my surprise. I knew we shared a common ancestor with chimpanzees. In a blink ago, I knew that we were genetically very connected to chimpanzees. But there was this disconnect between what I thought of as human disease and animal disease. But one of the fathers of modern medicine, Rudolf Virchow, wrote in the 19th century, between animal and human medicine, there is no dividing line, nor should there be. The object is different, but the experience obtained constitutes the basis of all medicine. Well, that was then in the 19th century. But more recently, we've sort of forgotten that. And if you ask most physicians today, what is the connection between animal and human health, they will probably give you the answer that it has to do with zoonoses. These are infections, pathogens that pass back and forth between the animal and the human reservoir. And we certainly know that one compelling reason for human and veterinary medicine to be connected to each other is the reality that at least 60% of the emerging infections that can affect human populations are coming from the animal reservoir. We're talking about, West Nile virus and SARS and avian flu and Ebola, and I'm sure you're all aware of this. But I was going to the zoo and I was seeing all these other disorders, and so I decided to apply a very simple schema. If I saw it in a human patient, I looked for it in an animal patient, trying to think beyond infection and think about spontaneously occurring diseases in animals and see how much of an overlap we had. Sorry for the black font. I don't know why anyway. Do animals get breast cancer, prostate cancer, heart attacks, atrial fibrillation, Crohn's disease, melanoma, painful periods, menopause, sexually transmitted diseases? And of course, the answer is yes, 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 yes. Something well known to veterinarians, but less well known on the human medical side. Physicians are not taught comparatively. Veterinarians are. So there's this interesting disconnect. The potential for thinking in this comparative evolutionary way is great. There are scientific takeaways, there are humanistic takeaways. Some of the scientific takeaways that I think are interesting, I learned for the first time that fear can trigger syndromes that are associated with death in a number of animal species, long-legged shorebirds, rabbits, and some hoofed animals as well. And actually that tracks with a fairly well-known syndrome in human beings of fear and associated with cardiovascular syndromes that culminate in death. January the 17th, 1994 was actually the date of the Northridge earthquake. I was here in Los Angeles. Many of you probably were. You might not know is that on that date, this was actually published in the New England Journal a couple of years later, the number of heart attack related deaths, cardiovascular deaths, on the 17th in January 94 versus the same date in 93, 92, 91. So there is this syndrome in humans. Up until embarking on this project, I was absolutely unaware, although veterinarians knew this was information hiding in plain sight, that this phenomenon and probably the same or related mechanism exists in a wide range of species. This knowledge, simply this knowledge that there is this connection, immediately opens the door to all kinds of hypothesis generation. The book covered breast cancer and other cancers, and I had never considered until the project started the comparative aspect of breast cancer, but I now know that spontaneously occurring breast cancer has been seen in a wide variety of mammals. Mammals by definition have breasts. It's been seen in kangaroos and big cats and koalas and Tasmanian devils and beluga whales and rabbits and bighorn sheep. One thing that we focused on, which was kind of interesting, was the BRCA1 mutation. BRCA1 mutation it's a mutation on human chromosome 17 that is associated with an increased risk of breast and ovarian cancer. Certain ethnic groups are more predisposed than others. It was a surprise to learn that there are certain breeds of dogs, English Springer Spaniels, for example. There's a group of them in Sweden that carry the BRCA1 mutation and have an elevated rate of breast cancer. Interestingly, so in human beings, if a woman is at elevated risk of developing breast cancer, one option is prophylactic mastectomy. And you probably are aware that Angelina Jolie did that, several months ago. But one of the other options is oophorectomy. So that would be having the ovaries removed, because presumably estrogen is going to drive some of these cancers. Well, it's interesting that in Europe, where companion animals, they don't have the same spay-neuter culture that we have. Most of our pets, if you have a dog or a cat, if you're a responsible owner, most of us spay-neuter our animals. By doing that, we remove hormonal influences, and the rates of breast and ovarian cancer are actually lower, and prostate cancer are lower in our companion dogs and cats than they are in Europe. But interestingly, there are certain big cats, particularly jaguars and tigers and lions, jaguars particularly, D. Macalus, who wrote this paper, looked at and these are animals that are in captivity who are being treated with progestins for contraception, have significantly elevated rates of breast cancer and ovarian cancer. And as of the Ubiquity Conference in New York last week, I learned that they presumably carry, she's pretty sure, this BRCA1 mutation, and that is probably mechanistically linked. And again, I'm not an oncologist, I'm not a breast cancer specialist, but this kind of knowledge that there's this vulnerability and this shared sort of genetic influence, I think is just, it just really opens things up a lot, and it's not the way human medicine is taught. I mentioned sexually transmitted diseases, and obesity is another really great opportunity to think, if not evolutionarily, think ecologically. We now feel, and actually, Richard Jackson here, who is the chairs the Department of, I think it's Preventive Medicine or Environmental Medicine, he talks about obesity as a disease of the environment. And much of the time when we say that, we are talking about the built environment, right? We're talking about segways and elevators and cars, right? And easy access to high calorie, low nutrition food, that kind of thing. And that is probably why our companion animals are getting fatter too, right? We're exposing them to our obesogenic environments, under-exercising, overeating. But it is interesting to consider this concept that there could be other environmental factors that we might not be thinking about. And there was one article called "The Plurality of Obesity Epidemics." that looked at increased body mass index in a number of species, and a couple of different rat species, one of which were sort of city rats, which not unexpectedly were getting heavier as they were eating our refuse, which was higher in calories, but the feral rats were also getting fatter. And so that allows us to speculate about endocrine disrupting chemicals and climate change and sky glow and who knows what. Maybe none of those are applicable. Maybe all that matters is calories in, calories out. Maybe the microbiome doesn't matter. Of course it does, but maybe it doesn't. The point is that if human obesity investigators are unaware that there are pockets of obesity emerging in non-human populations, there is no opportunity to generate a hypothesis that takes in a broader perspective. So we're just saying, knowledge is power. Well, I'm going to really go through this quickly because I'm running out of time, but we also decided, Catherine and I decided to look at psychiatric disorders, OCD, separation anxiety, eating disorders, self-injury, intoxication, and again, we found that animals, both domestic, farm, and wild, engage in many behaviors that are, if not identical to human psychopathology, are connected, and I suspect mechanistically and neurobiologically connected. From anxiety syndromes, there are some fascinating connections between human and canine separation anxiety, to certain forms of self-injury. Feather plucking disorder is not an uncommon syndrome that parrot owners talk about, some other birds as well. And they typically do it when they're distressed, when they're isolated. And I don't know where it happened to my trichotillomania picture, but the next picture is supposed to be a woman who's plucked out a lot of the hair of her scalp. And there's a syndrome called trichotillomania we see on the human side, which is a compulsive syndrome in which mostly women, sometimes men, mostly women pluck out either eyelashes or scalp hair or any pubic hair. And when you talk to people, and we have both veterinary behaviorists now and bird owners who have had birds who have this problem, and you talk about the triggers and the interventions, and then you talk to a human patient who's a trichotillomaniac and talk about what precipitates it, what exacerbates it, what attenuates it. Again, at the risk of anthropomorphizing, at the risk of overly projecting, I think there are some connections that are hiding in plain sight that argue for at least a hypothesis that links these mechanistically. And from a very practical perspective, and this is not explicitly evolutionary, but watching what animal experts do to treat these problems can actually have a different kind of translational impact on how psychiatrists and psychotherapists and parents deal with things. This is the patient that I was looking for with trichotillomania. Even self-injury, I'm sorry for the gory picture, but self-injury is not uniquely human. There are some very interesting things that I've learned recently about why it happens in animals, and I have to say that aside from the scientific and medical excitement that I feel about bringing this information to people to create their scientific hypotheses, there's this other, I think, really important takeaway, which is mental illness is highly stigmatized. 1 in 4 people in the US, at least, will have some form of mental illness, whether it's depression or bipolar disorder or schizophrenia, addiction, ADHD, Alzheimer's. Mental illness is very common. It's highly stigmatized. Highly. People don't get treatment. People are ashamed. There's self-recrimination. There's a lot of negativity. And I do think that this comparative perspective, the fact of comparable psychopathology in animals, has the potential to destigmatize mentally ill patients, but that's a side issue. And then even intoxication and addiction. There are, as you know, many species of animals that are known to ingest either inebriating, hallucinogenic, narcotizing substances and become intoxicated. These are waxwing birds. This picture was given to me by Emily Beeler, who is a public health veterinarian for LA County. And this was a group of waxwings that had gorged. Waxwings are notorious for eating fermented berries and getting intoxicated, and they fly around erratically. And Yeah, and then people laugh when I say that, and then I see this slide. But like human beings who become intoxicated, they are susceptible to injury. They fly into buildings, and this group of waxwings died traumatically. And you can actually see on necropsy that the bird, they gorge on these berries, and her gullet is just packed with these fermented berries. In the book, we have many examples of animals seeking out substances. The nearly iconic stories about the Tasmanian wallabies that get into the poppy fields and eat the poppy sap and the poppy straws. Eating disorders I'm going to move through. Because what I want to do, these are posters from these conferences that we've been hosting. We're trying to, Catherine and I, and Dan was a keynote at our first Ubiquity conference, and others have been involved. We're really trying to pull together the human and the animal community to look at the shared disorders and hopefully develop collaborations. So we've had two Ubiquity conferences here where UC Davis School of Vet Med collaborated with us along with the LA Zoo. And this is actually the dean of our medical school, Gene Washington, and this is Dean Benny Osborne, who is the dean of UC Davis Veterinary School of Vet Med. So this is the kind of handshake we're trying to duplicate. And then 2 weeks ago, we had our third Ubiquity conference in New York City. We had the Wildlife Conservation Society, the Animal Medical Center. It was a great time. And we had Harvey Feinberg there, who's the president of the Institute of Medicine, and he was expressing his interest in evolutionary medicine in his keynote. So that was exciting, connecting this kind of comparative approach to the evolutionary approach. Well, ultimately, as I said in the beginning of this talk, what do we need? We need the killer app. We need proof of concept. The only way we're going to bring physicians into this conversation is we're going to have to make the case that it's worth their while. There are already some very exciting examples with great potential. Andrew Reed, who is an evolutionary biologist at Penn State, was here, and he gave a great grand rounds about the potential for developing evolution-proof antibiotics to sort of conquer the problem of antibiotic resistance. I mentioned earlier thinking about Steve Stearns and others who are thinking about coronary heart disease and diabetes, and thinking about the developmental and the epigenetic origins, the influences on metabolic syndrome, etc. And then again, this very exciting idea of ecologically informed chemotherapeutic strategies. So, one approach to dealing with certain tumors is to actually embolize the arterial system that feeds the tumor. The idea is to starve the tumor and kill it in that way. And that may work, it may not, but if what you're doing is not completely killing the population of cells, but depriving the population of resources, is that actually an adverse thing to do? Could that inadvertently, iatrogenically cause dispersal, i.e. metastasis? And then Randy Nesse, who wrote the wonderful book, Why We Get Sick. Randy is a psychiatrist. He's a clinical psychiatrist, and he's University of Michigan. He just literally about 2-3 months ago started an evolutionary medicine program at ASU, and he has looked at panic disorder and talks to his patients about their panic and explains it in an evolutionary context, and explains that that a robust adrenergic response to threat is maladaptive in contemporary times, but that is something that the patient's mammalian ancestors needed. And he's very articulate, and he's very kind in how he talks about talking to his patients. But actually, he believes that that the evolutionary explanation per se, that is an intervention which can be palliative. That for some patients, understanding they're not dying, what they're experiencing physiologically is an evolutionarily anchored experience, can be therapeutic. So that's interesting. But what I want to do is talk about congestive heart failure in the 5 minutes I've left myself. Because congestive heart failure, I think, is a great example of a very important clinical syndrome that has the attention of the human medical community, for sure, and that underwent a revolution about 25 years ago that resulted in a significant reduction in mortality and morbidity. And one can frame that revolution in evolutionary terms. And what I'm going to do is to quickly go through this and ask the question, let's say it was 50 years ago. Had evolutionary medicine been a basic science, and had we been seeing, this over 50% 5-year mortality over and over and over again, if someone had asked the question, what evolutionary principles might be at play that are contributing to this high mortality? Is there a mismatch? Is this a life history trade-off? Are there selective pressures? If someone had asked that question specifically, is this a situation where something that is adaptive is now maladaptive, a kind of mismatch of adaptation, maladaptation, might we have accelerated this revolution? So what is congestive heart failure? Okay, my video won't work. So congestive heart failure is a syndrome where the ventricle, and there's lots of different kinds of CHF, but the classic ventricle, which is supposed to squeeze like this, gets injured. And so instead of squeezing, this is what we call an ejection fraction of 65%. So it's vigorous. The ventricle gets injured. And in the US, the most common way that the ventricle gets injured is from a heart attack, right? An acute blockage of one of the coronary arteries. And so the function goes down. All right. When the function is reduced, what happens? The perfusion pressure is decreased. So the baroreceptors in our great arteries and our kidneys, right? So the kidneys maintain the kidneys regulate our volume status. When there's low perfusion to the kidneys, to the juxtaglomerular apparatus, that triggers sodium retention, and it triggers the release of catecholamines, adrenaline-like substances that lead to vasoconstriction, right? When there's hypoperfusion, that means that your blood pressure is low. And you want to hang on to your sodium, you want to hang on to your water, and you want to shunt blood to your central organs. And that's what you typically see. And we do see that. When there's a reduction in ejection fraction, that's what starts to happen. And I'm going to get back to that in a second. This is a huge issue in the US. There are more deaths from heart failure than all forms of cancer combined. There's 550,000 a year, projected by 2037 to be, massive numbers. Mortality, over 50% of patients will die suddenly, causes or contributes to over 600,000 deaths per year. As we get older, there's more heart failure, and the population is getting older and older, and consequently, heart failure is a public health crisis and anticipated to continue to be one. In association with decreased ejection fraction, we see lots and lots of sudden death, and sudden death is defined as natural death due to cardiac causes, which is typically heralded by abrupt loss of consciousness, and sudden cardiac death is a massive issue. There are about 450,000 people who succumb to sudden cardiac arrest per year. It's equivalent of 2 747s going down every single day. And sudden cardiac death connects to congestive heart failure because we see a lot of the mortality from heart failures from sudden death. Okay, how does this connect to evolutionary biology? So the problem, when I went to medical school, which was in the early 80s, we were taught, I remember, that heart failure was a problem with the pump. A ventricle was a pump. And when the heart is injured through a heart attack or toxins or alcohol or viruses, the pump, instead of working like this, works like that. And so the therapy was to flog the pump. We gave inotropic drugs. Those are drugs that improve cardiac contractility, like digoxin, digitalis, Lanoxin. Every heart failure patient was on dig. We gave intravenous inotropes, these phosphodiesterase inhibitors, to pound the heart, right? But it turned out that didn't do very much. And when I graduated from medical school, the mortality associated with heart failure was above 50% in 3 to 5 years. So it was worse prognosis than many forms of cancer. But one can look at that death rate as a failure to recognize a fundamental evolutionary tension between something that's adaptive and maladaptive. What ultimately kills patients, it turns out, we now know, who have heart failure, is not that the the pump isn't working well. The problem is not that you should flog the pump. The problem is that the decreased perfusion to the kidneys and to the great arteries triggers a response which is very adaptive to hypoperfusion due to trauma, exercise, hemorrhage, exsanguination. Under conditions of trauma, let's say hypovolemia, hypotension, low blood pressure because of internal or external trauma, there's going to be low perfusion pressure, and what you want to see is vasoconstriction. You want to see a tachycardia, a high heart rate. You want to be retaining all the sodium that you can. You want to keep your volume status up. By the way, this is more than a hypothesis, because if you work in the emergency room and you see someone coming in after a massive motor vehicle accident or a gunshot wound and there's a lot of blood loss, we often give patients, we try to maintain a blood pressure, we're trying to get them to vasoconstrict so that the blood can be shunted centrally to the brain and heart. And sometimes patients who are on drugs that are vasodilators, which I'll explain to you why we put them on for heart failure, we can't get control of their blood pressure. So it becomes, we know that under conditions of trauma and dehydration, that response is appropriate. The problem is that in a chronic setting, if you have a heart attack and your ejection fraction is reduced, that response is maladaptive. And what we see is this neurohormonal activation that leads to hypertrophy, change in the geometry of the ventricle, and sudden death. And I just want to show you, I'm not going to go into the proliferative pathways mediating repair and cardiac hypertrophy, except to say that these pathways are appropriate under conditions of trauma. You want to have proliferative growth hormone promoting cascade pathways activated under traumatic conditions. But under chronic conditions associated with heart failure, all this pathway does is to cause the heart to get thicker, which really screws with the energetics of the muscle, which leads to more fibrosis and remodeling, and it's a mess. And this is the real disease of heart failure. It's not that the pump is injured, it's the body's response. This maladaptive, neuroendocrine, sympathetic hyperactivation is what kills people. How do we know that? We know that because when we finally inadvertently, serendipitously stopped flogging the pump and started giving drugs that countered this neuroendocrine activation, we started saving lives. We started treating patients with ACE inhibitors, which counters this part of this activation, beta blockers, which counters this activation, and in fact, and with other drugs which do the same thing, and we saw reduction in all-cause mortality, reduction in morbidity. We saw decreased rates of reinfarction, and this is kind of a summary of a lot of these clinical trials. They're all given funny little names, Trace, Hope. They're odd acronyms, but ACE inhibitors, angiotensin receptor blocking drugs, beta blockers, all of these are targeting this neuroendocrine activation. And we're talking about sudden cardiac death risk reduction. Major success story in terms of heart failure. We now understand that the neuroendocrine response, which evolved to maintain cardiac output, this is from Peter Harris in 1983, during exercise and to support circulation when cardiac output falls after hemorrhage, becomes harmful when they are sustained and therefore are deleterious in chronic heart failure. And this began a true revolution in therapeutics for congestive heart failure. It is an adaptive versus maladaptive argument, and I'm going to end by suggesting that had we been thinking in this way decades earlier, beta blockers existed for decades before we learned that they would be helpful in heart failure. they used to be contraindicated in heart failure. Now you can't not have someone on a beta blocker. You better have a damn good reason, or they'll call the lawyers. The point is that had we been thinking from an evolutionary perspective, maybe we could have accelerated this, and maybe this story is one that can kind of inspire us to think evolutionarily about other medical problems. Thank you for your attention.
Couple quick questions.
Yeah.
I was wondering on this expert here, evolutionary process, it takes longer time, but how we can separate between evolutionary process, which is going to take longer, much longer time than all this environmental effect of pollution, food quality, like yesterday, every day by trying to get to 405 from life sciences to 405 take me 25 minutes. So I think we should declare this is evolutionary process, and this is environmental process, which is involved. You can call it ecological medicine or whatever. Or probably what is if the temperature is going to be increased of 2 more degrees Celsius in 50 years. So how this will affect the ecology of microbial activity. So still, I think I would think this we need to be careful to say, okay, there's evolution. I mean, we know how much medicine, experimentation, technology, knowledge lost 100 years. I mean, it's going so fast. But evolutionary process, I think, it will take longer.
Yeah, I actually prefer the term ecological medicine to evolutionary medicine. It's not as sexy in a way, but I think it's more accurate. And I think that one of the huge problems in human medicine is that we don't think ecologically at all. So much so, I mean, forget thinking about the microbiome. That would be that we don't think about. We typically think about an individual patient and not about a population. Unless you're an epidemiologist, you don't think about populations, and we don't think about the environment in which the human animal is living when they go home. We often have patients next to each other in rooms with infectious diseases. I mean, we don't think ecologically.
Yeah, just to supplement, I was reading actually a few days ago. It says from 5 to every 3 heart attack patients, they spend 1 hour or longer behind the wheel. So
Right.
this is something I think is very important to talk to.
Yeah, I mean, that reminds me, one major question in medicine we don't know in cardiology is, so sudden cardiac death is an arrhythmia. You have, one day you're fine, and then, you're fine at 107, and then at 121, you have a ventricular tachycardia. Why? What happened? What happened the minute before? We don't know. And it's really an unknown question, and it's a very potent question, and there are undoubtedly environmental factors that are triggering, and the way medicine is structured, we're looking so reductionistically. It's like the opposite of being ecological. It's very, very narrow. So, yeah.
I think this is awesome, and having taught pre-meds evolution, I've been often frustrated with some of their reluctance to recognize how important it is, and it's just a requirement, and they just needed the units in that class having to be open kind of thing. I mean, they told me this. So I think this is great, but there are also going to be some limitations to how many MDs you can take to the zoo and how many evolutionary biologists you can bring into the operating room, things like that. So is there also a push across medical schools to either have these evolutionary medicine classes as part of their curriculum or require it for admission?
Nope. We're going to have to. It's our job. We're going to have to either do or not do, demonstrate that it's worth a medical school dean pushing out another course on domestic violence or substance abuse or something that's very, very important. We have to demonstrate that it's important. I mean, there's a lot of things that are important, but and frankly, one thing is that now the MCATs have explicitly have evolutionary content in them as of this year. There was, in fact, the big moment, in essence, centered around a thing that Stanley Kaplan had included evolutionary content in their prep materials. So, but no, it's not common at all. And we're trying to be pioneers.
Yeah, so thinking about the case that you just described in the history of the development of treatment for arrhythmia and so on, makes me think that maybe, I mean, we've had this conversation before about one of the problems is how you get the care, right? And not because they're arrogant or uncaring, but because they're busy and they have real pragmatic responsibilities. And the imperative to do no harm, it seems to me, is perhaps one lever that we can use in that regard. And I think in order to show people the potential harm of some contemporary standard medical interventions, we have to broaden the scope to show the relevant comparative base. So I'm thinking here of the effects of contraception on risk for endometriosis or uterine cancer because of the resulting high number of menstrual cycles over the course of a woman's reproductive life compared to natural fertility population. And I mean, standard safety tests for, say, hormonal contraceptives might compare something like prophylactic methods, right? That's the wrong comparison group, right? The right comparison group is a natural fertility population. And there are so many things that are different in terms of what that population looks like from the perspective of the standard, clinical trial that it really requires people to think pretty differently about what they're doing. But if you point out, whoa, this therapy that isn't even seen as a therapy, it's seen as on the equivalent of taking vitamins or something like that, as a very low risk intervention, might have deleterious effects. If you look at the right comparison population, then people start to, it seems to me that if you take seriously your responsibility to do no harm as a physician, then you might start to worry, okay, wait, now we have to think more carefully about what we thought was a safe intervention. And there may be other cases like that where a rethinking, instead of waiting for history to show, oh, gee, we thought we knew and it turns out we were wrong, right? Or rethinking earlier on might grab people's attention. And I'm curious whether you have in mind other cases like this, where the things that people accept is this is the standard therapy now, but looking at it from an evolutionary perspective suggests it might not be a good idea.
Yeah, I mean, some of the ones that, I think the whole cancer arena is really, we've heard some pretty smart people thinking about creatively different ways of prospectively creating trials, like moving away from a scorched earth chemotherapy approach to a more kind of chronic disease model. Yeah, obviously I use the congestive heart failure one because it's like I want to claim evolutionary medicine as as having kind of cracked the case, but of course it didn't. The idea is exactly what you say, is to prospectively identify some targets, create some experiments, and demonstrate it. The one place that I think is just, comparative medicine has so much potential, but most of the time, if you're a clinical physician, you're not thinking comparatively as a source of information. Mostly, you're looking at clinical trials, and which is appropriate, but yeah, I'm excited about exciting my colleagues because they have really big brains and they know lots of things that I have no idea about, and I feel like this approach in their bigger brains can...
Collective intelligence.
Yeah.
Why don't we wrap up now? Second, but some people have to leave. Let's thank Barb again.